we decided to put together one of these crazy rocket sleds or supersonic sleds. Now, you're going to see that we used a certain tone in this thing. As much fun as that movie was, we decided to take a comical tone in this thing. The elements in the scene are funny, they're comical, they're fun to play with. The pilot and the sled, they're supposed to have a comedic flair to them. So a little different from things we've done in the past. We're trying to make everything look really real. So here's some of the reference that we used to put this rocket sled together. You can see an actual chair, actual pilot behind this little windscreen. You can see how fragile these systems were. Big, giant rocket engine. We love that big, complex engine in the lower left corner. Gosh, we had to use that. So Cam, who's our visual artist, visual development artist, put together some ideas, some sketches of what this thing could look like. And in fact, initially, we've got this thing up in the upper left corner. It was this kind of sleek-looking rocket. But we decided to actually fit the tone. We wanted something a little rickety, a little fragile, a little like it was just about to blow up. So we went closer to this design here at the bottom, and you see the 3D model here on the right side. Here's some of the evolution of that model. You can see we added some textures. You can see some of the complexities of things like the ejection seat with the rockets on the back, and some of the very detailed work. This is the suspension arm that attaches to the train.
It's a little ridiculous about the suspension arm. There's absolutely no reason for it. And virtually all those rocket sleds were completely rigid in their chassis and the relationship to the rails. And we wanted something that really was going to allow for a great deal more yee-yaw reaction in the way the physics apply forces to this thing. And it creates a much more alive feel to the sled that forces down the track. There's enough backward force. The back end of this thing actually tries to take off. And it does a lot of these, they're subtle by comparison to things blowing up. But not subtle, relative to the sled. It makes it very hard to control, and that's a large part of the fun. But yeah, the design actually did need to function. And I'm not a mechanical engineer by any means, but there seemed to be a logical way to apply what amounts to a shock absorber or a kind of pneumatic or hydraulic type of shock to these struts, these arms that the thing, the chassis is attached to. And lo and behold, our genius modeler, Chris, put the thing together and it worked. Who knew?
So this is all the visual development that went into this thing. But I mentioned right at the get-go that a big piece of this demo was the physical side, the physical simulation. So you're going to see, as we demo here in a moment, a whole lot of fluid simulation, particles, debris, all these things that are being computed all in a GPU. And I'll show some of these in detail. So we've got some great smoke coming out the back of the sled, billowy, big, huge smoke as it takes off. You can see some of the dust that's kicked up by the sled as it starts picking up speed down the track. And of course, it does blow up. Bad things happen to our pilot. And all the steam particles, the smoke particles, the fire particles are all GPU based. So here's a quick explanation. So surrounding the rocket sled at all times is a fluid solution. And as the rocket takes off, we're essentially injecting particles, smoke particles, into that fluid solution. And the fluid solution is influencing the motion of these particles, these smoke particles, as they're moving around inside that box of environment. It's not just constrained to the box, though, of course. As those particles leave the fluid solution, they maintain whatever velocity they had when they left. So you can essentially fill the screen with smoke. Likewise, I'm not showing you here, but this box extends all the way to the front of the sled. That's because as it picks up speed, that's where we start injecting dust particles into the fluid solution. Now, we take into account the mass of those particles, so you'll see that the smoke can actually rise, but the dust stays pretty low to the ground. But they're all being immersed into this fluid solution. Okay, so beyond just the exhaust coming out of the sled, there's GPU particle systems that are being computed whenever this system blows up. And you can see literally thousands of steam and smoke and dust and fire particles. Again, all being computed on the GPU. But as Cam alluded to earlier, the sled itself is also a physics object, it's a physical assembly. It's not just this graphics thing. So here's a close-up of that essentially foot that rides along the rail. You can see the visual development here on the left-hand side, but there's also a model, an internal model of its physics. And it's really simple. Remember I said there's this discontinuity for physical simulation? We're kind of at the bottom of that discontinuity and just starting to create stuff. So the physics simulation really is just a bunch of blocks, a bunch of cubes, and they're connected by some joints. These have some revolute joints that allow them to spin, but very simple. However, when you take a lot of these simple objects and you put them all together into a full assembly, you get, in this case, hundreds of objects being connected by hundreds of joints. Some of those joints are just constraint joints, glued together but allowed to break. And some of those joints are articulation. They can spin and turn and revolve.
And actually what we found just right away when we got the first model is when you actually connect everything together the way it is modeled, it's not very physically sound. It's not very structurally sound. Every one of these components experiences extreme forces and just breaks off. For example, the engine mounts, or the thing behind the seat in the front, that bears the entire load of the force of the thruster and the solid rocket boosters. And when we ran the first simulation, the thing just tore itself apart. And we had to do all kinds of tricks and sort of little massaging to get the system to actually stay together and function as a sled.
What I like is you can see the little harmonics there, right? That's all accurately calculated.
That's right. That's right. So an important point here is, except for one exception, and I'll talk about that exception in a minute, nothing in this demo is animated. Nothing. Everything is simulated. So as you see this rocket moving and vibrating and shaking as it's trying to go down the track, that's all simulation. No artist touched that motion. That motion is being simulated. Okay, so there's no animation in this entire demo, even though lots of things are moving around. There's one exception. I'll show you that exception in a minute. So I should also point out that there are items in the physical model that aren't visible. Right? So I'm pointing out this box, this bump stop. So there's, in the physical model, there's a stop that keeps that arm that's riding on the rails, from coming up too high. And it's essentially a block that just stops it from happening. You don't see it, but it still is in the physical model. So you're not limited to the visuals when you create that physical model. And last point on this slide, so we're actually computing the physics for this assembly on the CPU. That's not a typo, that's the CPU. Okay, so PhysX is running and computing all the position of these objects on the CPU. Now it's important that there's a handshake between the CPU simulation and the GPU effects that are going on. And one of the keys to that handshake is the authoring. So when we put this model together, we identified different pieces of that sled that are emitters. Essentially they can emit smoke or fire or whatever when they break. Now the CPU, as that sled's going down the track, is computing the position of all those objects and computing the forces on their joints. And at some point, they break. The forces exceed the joint's ability to stay together and it breaks. All that's going on in the CPU. But when that break happens, it notifies the GPU, the solution that's going on the GPU, and said, hey, this item broke. The GPU knows it's an emitter, so it starts emitting smoke. In fact, it remembers the history of that smoke. So for every frame we come out and draw, all the smoke and fire, whatever got emitted from that object, gets drawn on the CPU, and the GPU doesn't really know anything about it. So it's this handshake between the two simulations. Okay, that's the sled. Any questions on the way we put the sled together? All right, let's talk about the guy driving or riding the sled. So this is the pilot. Here's some of the reference that we use. On the left-hand side, these are the real military pilots that they used back in the 50s. But we wanted this thing to be comical and fun. So we actually went to another 50s, I guess 60s character. This is a guy named Don Knotts, for those that don't know him, and very famous for a character called Barney Fife, from the old black and white TV show. Anyway, he had the perfect bulging eyes and really animated facial expressions that we wanted to use for this demo. So we modeled our character after that type of personality and physical design.
We knew we were going to be thrashing this guy again and again and again. And to make him too realistic, it just seemed rather grim. And that was a big push to make it, to take a more humorous approach to the character.
And again, so here's some of Cam's artwork as we did the visual development of this guy. You notice there's this little scientist man. He doesn't show up in the demo. That was an early concept. We were going to have a scientist involved in this thing as well. But we abandoned him and just decided to punish the pilot alone. By the way, that pilot's name, Barney, after the Barney Fife character. So Barney is actually made up of physics objects as well. So his entire skeleton is these sets of blocks. These blocks are connected again by joints, and it's fully simulated. Again, no animation going on here. It's a fully simulated model. You can see the objects that we use. And this is just a quick sort of geeky slide. Each of those objects have joints, and those joints have range of motion, right? So your wrist can only go so far. So these little cones that you're seeing are the ranges of motion that physics allows for these objects. And so because these are simulated objects, it allows us to do this ragdoll fun. Ashi talked about ragdolls earlier. So he actually interacts with the whole scene. His body, in this case, we had some fun. He will wrap around the sled seat, gets stuck on the engine, he gets tortured. Okay, so pilots back in the 50s didn't have much wind protection on these sleds, so their face is really distorted. This is a great example of some poor guy going through one of these rocket sleds. So our pilot Barney, we decided needed to have the same effect happen. So here on the left, here he is all excited and ready to go. And then these three shots on the right are some of the distortions that his face goes through as he's headed down the track. Now I mentioned earlier that there's nothing animated in this entire demo except for one thing. This is the one thing. So we animated his face. But what's interesting, even in doing that animation, we used that cloth and clothing demo that Stephen was showing earlier. We actually used that to do these rippling deformations in his face, to use those as blend shapes for the animation. So this face is essentially made of cloth. We use the cloth simulation to do it.
I do have to add, you guys will notice when you see the demo that his body and his hands and arms and his behaviors when he's not in ragdoll are also a series of animations that are chained up and put together that are triggered by various physical events around him. So they're still tied into the physics in terms of if something happens, a particular force turns a certain way, then that causes another animation of the chain of behaviors to take place. But you know, it's quite obvious that the pilot himself is animated in his behaviors until he hits ragdoll. And at that point, all animation ceases and it's all physical.
Okay, so we got a sled, we got a pilot. Now we need to focus on the environment that they're in. I'll let Cam explain some of the things he was thinking about with the environment they're in.
Yeah, I have a background in visual development, concept design for film, 3D animation, this type of thing. And I use precisely the same process for these demos that I did working in film. So we started out with doing a variety of drawings for the environment to get a general feel. I did a bunch of different iterations of that. And then, if you want to hit the next slide, then we did a color treatment. You get a sense of what the shaders were going to be up against, what kind of atmosphere we were going to have, various issues like that. We did a bunker set where the launch pad was going to be kind of complicated, so I did the same thing there, did a full 2D rendering of all the different things that we were going to need to consider. And then of course that informed the textures that were eventually applied to the 3D models. And a good deal of consideration was put into what sort of physical gags we might engage in as we go down the track. The sled is going to need to encounter some things. We wanted some hazards and some physical things that would occur. Not only that would threaten the pilot further than the sled itself, but it also would give the user an incentive to really go fast. Because if you break the sound barrier relative to some of these objects that you encounter going down the track, you'll physically influence them by the sheer force of the sled passing it.
The demo team has this huge love of the talents of CAM, but sometimes it's a struggle to make the actual real-time environment look as good as what you can draw up.
They do
And
great.
you can-
They do great.
And you can see in some of the quality of these illustrations, it gives us a great target to shoot for. Sometimes it's a stretch goal to get there, but it's great to have some of it. Okay, so we talked about, so these are three physical elements in the scene. And I think you saw the demo earlier, so you know what these are. But all these elements essentially use the same kind of physics simulation. I'm just going to focus on the bridge as one example of it. So we talked earlier about this handshaking between the CPU and the GPU. The same thing's going on in these elements. So here on the bridge, as the bridge blows up, these large girders and beams and big steel items are all physics simulated on the CPU. And in fact, those items can collide with the sled and destroy it. But added to that, to give it some more realism, are the dust particles, these small chunks of debris that give it some more, make it more interesting as this thing blows up. And in fact, because we can generate and draw so many of these things on the GPU, where we got about 1,500 objects on the CPU simulator, man, I can put thousands of these little debris chunks generated by the GPU. And in fact, we thought, gosh, how many can you do? 10,000, 20,000? Here we're doing 40,000. How about 1 million? So just for fun, we just cranked the physics as high as we dared go until we had what I call a ridiculous amount of debris on the scene. Clearly, there's more debris there than there ever was bridge to start with. But the fact of the matter is, we can we can simulate and draw 1 million debris particles at a reasonably interactive rate. I'm not going to say this is super fast. We'll show it to you here in a minute, but it's reasonably interactive. So 1 million debris particles. And in fact, one of the cool things about these is these debris particles will actually they'll properly fill in the terrain. Wherever there's a crevice in the terrain, you'll see these debris particles fill it in. So it's crazy, it's way too much. And it clearly doesn't go with the scene, but it's 1 million particles. All right, so talking a little more about the terrain design, you saw in that movie at the beginning, they used this mesa called Hurricane Mesa in Utah, which is flat, completely flat. It's kind of boring. So we jazzed it up again a bit by putting in some mountains and some buttes and some rocks and things. Also, it's important to point out this rocket is going 800 miles an hour or faster. So we had to have for it to last 20 seconds or so, we had to have a really long piece of terrain to work with. So you're going to see this is a big area. And this map basically points out where some of the physics, environmental effects are going on. But this thing is miles and miles long, which presents a challenge. That's a lot of data, a lot of geometry to have to deal with. One of the things that helps us out is tessellation. I know we talked about tessellation with you earlier today. Here's one of the places where we're using it. You can see this rather low tessellated mountain there on the left-hand side, and what the shaded mountain associated with it looks like. It's important to point out, this mountain has vertical or nearly vertical cliffs. You'd never know it by looking at this thing. because the height map or the displacement map we use for the terrain is being sampled so sparsely that what was vertical is quickly becoming sloped. Looks like a ski slope. Now when you crank up the tessellation, we go from something that looks kind of ugly and sloped. Now, our sheer cliffs are back, and you can see a lot more definition in the terrain. There's a neat feature in the tessellator that allows us to do to adjust the way tessellation happens based upon planarity. Essentially, two polys come together. The angle between those polygons will determine whether or not we further tessellate. So you can see on the left here, we've got a regularly tessellated grid. When I turn on planarity and tessellate, you'll see the area that's flat ground didn't get nearly as many triangles as the areas as you start heading up the sloped side of the mountain. Of course, we put effort into shading the terrain as well. And an interesting problem when you have something like this, you'd think you could use things like aerial photographs. If you're looking down on the terrain from an airplane, take that picture and just map it onto the geometry. That doesn't work. And the reason that doesn't work is because you have vertical cliffs. And as an airplane's flying over and takes a picture, guess what it sees? You know, it sees a couple of pixels that represents a huge tall wall. And so you just get this stretched, ugly look. We took an approach with the shading of the terrain. That's a tiled approach. For vertical walls, we use one kind of shading and texture. For horizontal surfaces, we use another kind. And for the transition between the two, we use yet another kind. We blend all those together, and we get the terrain that you see in the dome. This allows us to have both definition on the vertical surfaces and on the horizontal surfaces, and a nice transition. We're doing some work with haze as well, atmospheric effects. So you see as these mountains get off into the distance, there's haze. There's an atmosphere between you and those mountains. Last thing I'll talk about, because I'm done talking and you want to see what this thing looks like. We're doing some image processing as well on the demo. In fact, a lot of image processing. We're doing bloom shading. We're doing depth of field shading. And one of the very interesting things that you'll see is motion blur. Without going into gore detail, to do the motion blur, we capture, at every frame, we have the previous object's position, the current position, and the previous camera and the current camera. Knowing those four things, as we shade the object, we can output two things. One is the unblurred image, the image you'd expect to see if there was no motion blur. But at the same time, so we use this concept MRTs, which came out in DirectX 9, multiple render targets. At the same time, we generate a velocity buffer. That velocity buffer has a bunch of pixels that represent the speed of that pixel, essentially, at both the magnitude and direction of that speed in screen space. Okay, I'll show you a picture of it. Weird. Okay, but anyway, the velocity of every pixel. Then we do this image processing. Essentially pass a dynamic kernel that samples in that velocity buffer, knows the velocity at that point, will dynamically sample other pixels in the colored buffer based upon the magnitude of that velocity and in its direction, and come up with a interpolated coloring based upon those samples, and put that into the back buffer, which is essentially where we composite the final image. So what this looks like, here's a snapshot in time of the sled exploding. The camera's focused on the pilot pretty much all the time. So he is zero. He has no velocity relative to the camera. And you'll see in the upper left-hand corner, that's the velocity buffer I was talking about. So objects that are red or have a red look to them, they have some kind of horizontal velocity to them. Objects that have a green component to them have some vertical velocity to them. So as we sample into that color buffer, sample into the unblurred image, we start to create these. You can see there's There's no defined edges in here, and all this object is nicely blurred in the direction that the object is moving. Okay, so to sum it up, that's an Americanism, I don't know if that translates very well, the kitchen sink. Kitchen sink means it's got everything in it but the kitchen sink. It's our job as the demo team to exercise every square millimeter of new products that come out. The GF100 is a big beast. It's got a lot of neat features to it. So we get the opportunity to exercise it. So we've got physical simulation going on the GPU. We've got all the tessellation work going on with the feature of DX11 tessellation. We're doing all the environmental effects that I talked about, as well as this several image processing effects, including motion blur. And finally today, I'm hoping to show you it running in 3D vision. To be honest with you, we've had a few gremlins in here right before you came in, and we're hoping everything's going to go. Any questions on this? If not, I'm going to turn you over to oops, real quick question.
Will it be publicly available?
Will it be publicly available? Yes, that is the plan. We always release all our demos. And the one we're excited about, this particular one, is so interactive, I think people will enjoy playing.
A lot of our demos historically, I mean, they've been, you sort of watch them a couple of times and you see the cool effects and then, you sort of move on. But this is being built with a game where you can get scores and so we think it, will be something that people, that customers of the products will really enjoy. Being able to download the demo, play the game, and get high scores and compare them with difference.
Okay. All right, one more time. I'm going to make you all get up. And